Today we are going to discuss quantum tunneling. We have a particle which is free to move along the x axis, and there is a potential. The potential looks like this. It is 0 in the region to the left, and then here it takes on a value which is constant for some range of x, and then again it is 0 on this side, and this constant value let me denote by V. So, essentially there is a potential barrier V which separates the region to the left from the region to the right, and let us say that the potential barrier extends from x equal to 0 to x equal to a. Now, we will consider a particle of energy E which is less than the height of this potential barrier, and so this is the energy of the particle E, and a particle of this energy E is incident on this potential barrier from the left hand side. So, the particle is incident like this. Now, if you were to analyze this situation using classical mechanics, where we had a potential barrier V and there was a particle incident from the left hand side whose energy was less than the potential V, in classical mechanics we would expect that the particle would get reflected back. It would not be able to overcome this potential and reach the other side. The particle would get reflected back. So, if it were a macroscopic particle whose description is well described, whose behavior is well described by classical mechanics, what we could say is that definitely for sure the particle would come up to the potential barrier and then get reflected back. It would not be able to overcome this potential barrier. But what happens in quantum mechanics? That is the question that we are interested in. So, in quantum mechanics, if you are dealing with microscopic particles, you have to apply quantum mechanics, and for microscopic particles you have to use a wave to describe the particle. So, we have to write down a wave for the particle in this region. We will refer to this region as region 1. We have to write down a wave for the particle in this region, which we will refer to as region 2, and we will write down a wave for the particle in this region, which we shall call region 3. And we have already seen that if I have a particle of energy E less than the potential, and if it is incident on a step potential like this is a step potential. We have already discussed this. We have seen that the wave corresponding to this particle is going to penetrate inside this to some extent. So, in today's lecture we are going to see what is the consequence of this. So, what happens in such a situation in quantum mechanics? The left hand side, the region 1, in region 1 the particle is essentially free because there is no potential in region 1. So, let me write down the wave function in region 1 where the particle is essentially free because the potential there is 0. Let me indicate that here, or no, it is not required to indicate it. So, in the region 1 the particle is essentially free because the potential is 0, and I can write down the wave function in this region. The wave function in this region psi 1 x t is going to be e to the power minus I e t by h cross. The time part is going to be e to the power minus I e t by h cross. Remember that whenever I have a static potential, the time part of the wave function is always going to be exponential minus I times the energy into t by h cross, where E is the energy of the particle. We have seen seen this in a lecture quite a few days ago, that the time part is always the same in a static potential. So, this is going to be the time part, and the spatial part is going to be A1 e to the power I p x by h cross plus B1 e to the power minus I p x by h cross. So, the spatial part of the free particle wave function could have two parts. The first part, when I combine with the time part, we can see that it is a right propagating wave. The second part, when I combine with this, we can see that it is a left propagating wave. So, the term with A1 is a right propagating wave. It represents a particle going to the right. The term with B1 is a left propagating wave. It represents a particle going to the left. So, the term B1 represents a particle going to the left. Both of these are eigenfunctions of the momentum operator. We have seen that the momentum operator P is minus I h cross, the partial derivative with respect to x. So, it should be clear that both this and this are eigenfunctions of the momentum operator. When you act with the momentum operator on this, so when you act with the momentum operator on this, let me do it for you here. P, let me write out this thing, this part separately. So, the first part is A1 e to the power minus I by h cross E t minus p x. This is the first part, this part. So, you can see that this is a right propagating wave. It is a right propagating wave because as time evolves, the point where the phase has a same constant value keeps on moving to the right. So, this is a right propagating wave, and when I act with the momentum operator on this, the momentum operator is minus I h cross del by del x, acts on this. What I get, so if I differentiate this with x, I will pick up I p by h cross, and that is going to get multiplied. So, I already have minus I h cross over here, and if I differentiate this, I will get I p by h cross, and then I will have this e to the power minus I e t minus p x by h cross into A1, and we see that this is going to be minus I into I is 1, h cross will cancel out. So, what we are going to get is p into A1 e to the power minus I by h cross E t minus p x. So, what we see here is that this function is an eigenfunction of the momentum operator with momentum plus p. So, it should be clear from this that the second part is a left traveling wave, and it is an eigenfunction of the momentum operator with eigenvalue minus p. So, we can see that the first part represents a particle with momentum plus p, a positive momentum, which is the incident particle, and the second part represents a particle going in the opposite direction, which is the reflected particle. So, this is the wave function in region 1, where the particle is free, and I have also told you the physical significance of these two parts of the wave function. This is the incident particle, this is the reflected particle. And remember that if we were doing classical mechanics, all particles would definitely be reflected back. Now, we have already discussed the behavior of the wave function in this region, where the potential is larger than the energy. We have already discussed the behavior of the wave function in this region, where the potential is larger than the energy, and in region 2 the wave function psi x t is going to have the same time dependence. In all regions it is going to have the same time dependence, but in region 2, instead of having an oscillatory behavior, the wave function is going to have exponential solutions of this form: a2 e to the power minus q x by h cross plus b2 e to the power plus q x by h cross. There are two possible exponential solutions in this region, and they are e to the power minus q x by h cross and e to the power plus q x by h cross. Let me also tell you what these p and q are. We have discussed this in earlier lectures. Let me remind you what p and q are again. So, p is the momentum of the particle in the region where it is free, and this is 2 m e. So, the constant p which appears in the wave function in this region can be interpreted as the wave function, as the momentum of the particle in the region where it is free, and in this region the momentum is 2 m e, the square root of it, and q is square root of 2 m v minus e. Q is to be used in the region where v is greater than e, and q is the square root of 2 m v minus the difference in the potential and the total energy of the particle, and it is this q which appears in the wave function in region 2. Now, let us ask the question, what is the wave function of the particle in region 3? There are three regions. The particle is free here, it is also free here, and it is under the influence of this high potential barrier in this region, region 2. So, in region 3 also the particle is free, and we have already seen the free particle wave function. So, it is going to be the free particle wave function in region 3 also. So, I can write down what the wave function is going to be in region 3. In region 3, the wave function is going to be psi x t is equal to, the time part is going to be exactly the same, e to the power minus I e t by h cross, and I will have again two different amplitudes, a 3 e to the power I p x by h cross plus B3 e to the power minus I P x by h cross. So, in region 3 the wave function is exactly the same as region 1, except that these two coefficients of the right travelling wave and the left travelling wave are different. Now, let us again go back to the physical interpretation of these two parts. We have already discussed that this part, the first part, represents a right travelling wave. So, the first part represents any particle that may, any part of the wave that may get through. So, the wave is incident, the particle is incident like this. So, we have a right travelling wave coming over here, and then the wave behaves exponentially and it decays exponentially inside here, and the third part represents any part of the wave that may penetrate through this and come out in region 2. So, the third part represents a right travelling wave in region 3, and you can think of it as representing, this actually represents a particle with momentum plus p in region 3. So, it is any particle that can penetrate, so that can penetrate through this barrier and get out in this region. So, it represents a particle going to the right in this region, and we can represent that as the particle penetrating through this and coming out over here. Whereas this term over here, the second term having B3 is a left travelling wave in this region, a wave travelling to the left like this. It is a particle, this corresponds to a particle with momentum minus p. So, if I had a particle with momentum minus p over here, the particle would be travelling in this direction. So, it would represent particles which are incident on this potential barrier from the right. Now, I have already defined the physical situation that we are discussing. In this physical situation, we have a potential barrier and there are particles incident on the potential barrier from only one direction, from the left. So, we have this potential barrier and there are particles incident on it only from this side, and we would like to now study what happens to these particles. There are no particles incident from this side. There are particles incident only from this side. Some of the particles will get reflected, some may get transmitted. In classical mechanics, all the particles would get reflected. In quantum mechanics, we see that the wave function corresponding to these incident particles can penetrate through the barrier and some of it may come out, and then because of that we would have a finite probability of finding some particles here. So, these would be particles that have managed to somehow get through this, and they would be particles going to the right. Particles going in this direction would, if I had a part of the wave function going this way, they would correspond to particles coming like this. And they would be particles which are incident on this potential barrier from the right, but we are not sending in any particles on the potential barrier from the right. So, there are no particles coming in from the right, there are particles coming in only from the left. So, which essentially tells us that the amplitude of this part has to be 0, because this is the probability of finding, this gives us the probability of finding some particles with momentum minus p over here. Momentum minus p means a particle going this way, but we are not sending in particles like this. We are only sending in particles in this direction, and some of the particles may get through and come out this way, which is what this would represent. So, this tells us that this coefficient over here has to be 0. So, we have worked out the wave function in the 3 different regions in our problem. We have worked out the wave function in region 1, in region 2 and in region 3. Let me graphically show you these wave functions in the 3 different regions. So, if I draw the potential here again, the potential looks like this. And what we see is that on the left hand side we have a plane wave solution with 2 possible parts, one representing a particle which is incident, this representing a particle which is reflected. The main point is that we have plane wave solutions whose wavelength is determined by P. So, we can schematically show that like this, that we have a plane wave solution in this region, region 1. Now, in region 2, we see that the wave function behaves exponentially, and what we would expect if is that the wave function actually decays exponentially. So, in region 2, the wave function goes, some part of the wave function manages to penetrate into region 2 where the potential is higher than the value of the energy, and the wave function in this region decays exponentially. And then in region 3, we again have oscillating solutions. So, we have oscillating solutions here again, we have oscillating solutions here again, but the amplitude of these oscillating wave functions here is going to be much less than the amplitude of the wave function here, because the wave function decays exponentially inside this, and then finally some of it does manage to come out onto this side. So, what we see is that in quantum mechanics there is a finite value for the wave function in region 3, it is not going to go to 0 abruptly, and if you have a wave function, finite wave function in this region, then there is a probability, the modulus square of the wave function in this region tells us the probability of finding the particle in region 3. So, there is a finite probability of finding a particle in region 3. So, in quantum mechanics, when there are particles incident from this direction, there is a finite probability of finding some of the particles in region 3. So, some of the particles can get through this potential barrier, and you may find them in region 3. There is a probability, and this phenomena is what is known as quantum tunneling. The analogy here is like a hill. If I have a hill on the surface of the earth, the hill represents a potential barrier. If a particle has to cross this hill, let us say that there is a car which would like to go over the hill, then there are two possible ways which would like to get across onto the other side. There is a hill over here. The analogy is as follows: say on the surface of the earth there is a hill like this, and there is, let us say, a particle over here. We would like the particle to get to the other side. There are two possibilities. One, you give the particle sufficient kinetic energy so that it can roll over and get over there. The other possibility is if you have a tunnel which goes through this. So, then if the particle can go through this tunnel, it does not require to have enough kinetic energy to get over, and the particle can then go through this tunnel and reach the other side. If you have travelled by train to Mumbai, for example, you will find that there are quite a few tunnels on the way, and these tunnels basically make it easier for the train to get to Mumbai, because there are quite a few hills in the Western Ghat, and it would require enormous amount of energy to overcome to get to the top of the hill and then come down, and this can be avoided if there is a tunnel through the hill. So, it is as if a particle which is being sent on this potential barrier, the particle which is being sent here does not have sufficient energy to go over this barrier, but when you use quantum mechanics to analyze such a situation, you find that there is a finite probability that the particle may get through to the other side. This arises because you have now a wave description, and there is a possibility that a part of the wave actually penetrates through, because in this region the wave function does not abruptly go to 0, it decays exponentially. So, there is, and then once it comes here, again you have this oscillating solution. So, there is a wave function in this region which tells you that there is a probability that even if you have incident particles here, with energy less than the potential, there is a finite probability that you can find this particle on the other side. So, it is as if the particle has got through by making a tunnel, by somehow tunneling through this potential barrier, which is why this is referred to as quantum tunneling. Now, the quantity of interest is to which we would like to calculate is the probability of finding the particle on the other side. So, we are sending in particles from the left, and the question that which is of interest is what is the probability that of finding this particle which is incident from here, what is the probability of finding it in this region, what is the probability that it gets through the barrier, which we can refer to as the tunneling probability. So, we have incident particles coming in. What is the probability of finding the particle in region 3? This is the question that we are interested in. And how shall we address this question? Let us go back to the wave function in the 3 different regions. So, this is the wave function in the 3 different regions. This represents the incident particle, this represents the reflected particle, and this represents the particle that tunnels through and is found on the other side of the barrier. So, the probability of finding the particle on the other side is there in the coefficient, is in the amplitude of this part of the wave function. The larger this amplitude, the more is the probability of finding the particle on the other side of the barrier. So, this is the amplitude of the incident wave, this is the amplitude of the transmitted wave. The ratio of this amplitude essentially tells us we will get the probability amplitude from the ratio of these 2 amplitudes. The reflected wave amplitude is there in this. So, we will get the probability of the particle getting reflected from the ratio of these 2 amplitudes. How we will get it, we shall discuss later. Now, the question is how do we determine these coefficients which have been unknown till now. Remember earlier when I discussed potentials, step potentials, I did not go into the issue of how to relate the coefficients on the 2 sides, and I had told you that I shall be taking it up later. So, let us now discuss how to relate the coefficients, these amplitudes of the different parts of the wave on the 2 different sides of the potential, step potential. So, the governing principle is that whenever we have a step potential like this, whenever we have a step potential like this or like this, the value of the wave function should, on the left hand side, should match the value of the wave function on the right hand side. So, the wave function should be continuous across this step in the potential. So, let me write down the boundary conditions. So, the first boundary condition, as I mentioned, is that the wave function should be continuous across this boundary. So, let us consider the boundary at x equal to 0, the step at x equal to 0, and the value of the wave function on the left hand side, psi 1 x t at x equal to 0 should be equal to psi in region 2 at x equal to 0. So, at the boundary the wave function should be continuous. Also, the first derivative of the wave function, first spatial derivative of the wave function at the boundary, which is x equal to 0, should be continuous. So, whenever we have a boundary, whenever we have a step in the potential at any boundary, any such boundary, the wave function and its first derivative should be continuous. So, this is one region, this is another region, we have two different waveforms of the wave function here and here. At this interface, at this boundary, the wave function and its first derivative should be continuous. Now, you may ask the question, why should the wave function and its first derivative be continuous? Why not the second derivative? Why not require that the second derivative also be continuous, the third derivative also be continuous? The reason why we require only the wave function and its first derivatives to be continuous, and the reason why we require this is because the wave function is governed by the Schrodinger differential equation. The Schrodinger differential equation, remember, so let me write down the Schrodinger differential equation here. The Schrodinger differential equation is I h cross del by del t of psi is equal to minus h cross square by 2 m del square del x square psi plus v x psi. This is the Schrodinger wave equation which governs this wave function, and this equation has to be satisfied at every point. Now, the potential changes abruptly at the boundary, but this equation has to be satisfied everywhere. Now, let us first take the time part. The time part is the same throughout. The time part of the wave function is the same throughout. So, we really do not have to bother about it. We have to be concerned about the spatial part. The spatial part is different in region 1 and region 2. We are considering the boundary between these two. The spatial part is different in these two regions, and here we have the second spatial derivative. Now, to evaluate the second spatial derivative at the boundary, we need to first evaluate the first spatial derivative at the boundary, the first derivative with respect to x. Now, if the function psi has different values on the left hand side and the right hand side at the boundary, if it has a different value at the left and the right hand side, if it is discontinuous, then you cannot evaluate the first derivative. The function has to be continuous for the first derivative to be defined. So, the fact that you have to evaluate the first derivative at the boundary tells us that this boundary condition has to be imposed, this has to be satisfied. Now, you not only do you have to evaluate the first derivative, you also have to evaluate the second derivative at every point, so also at the boundary. To evaluate the second derivative, the first spatial derivative itself should be continuous. You cannot differentiate a function that is not continuous. So, in order that the second derivative is well defined, you require the first derivative to be continuous at the boundary. It is continuous elsewhere. You also require it to be continuous at the boundary, which is why you have to also impose this boundary condition. So, we now have two boundary conditions which have to be imposed at all boundaries. The time part is guaranteed to satisfy this. It is the spatial part that we have to be concerned about. So, we have to impose these boundary conditions, and it is these boundary conditions that is going to tell us how the coefficients, the different on the two different sides are related. You have two different boundary conditions, and these two different boundary conditions are going to allow us, in principle, if I look at the interface between this region and this region, these two different boundary conditions will allow me in principle to eliminate A2 and write it in terms of A1, B1. It will also allow me to eliminate B2 because there are two boundary conditions. So, I can eliminate A2 and B2 and write them in terms of A1 and B1. Similarly, if I look at the boundary between region 2 and 3, I can eliminate B3 and A3 and write them in terms of this. So, finally, I can express the coefficients in all three regions solely in terms of the coefficients in region 1. So, there are two unknown coefficients which are going to be there, only two unknown coefficients. All the other coefficients can be expressed in terms of these. So, this is what we are going to do in the rest of the exercise. We are going to find relations between these coefficients, and then finally, we are going to use this to calculate the probability that the particle can get through this barrier. The probability that the particle can get through this barrier is going to be decided by the ratio of this coefficient to this coefficient. In doing this calculation, we are going to make a simplification, and the simplification that we are going to make is as follows. We will assume that the potential V is much larger than the energy. So, we are going to assume the height of the barrier is much larger than the energy of the particle. So, in this picture, we will assume that this V, this height of this potential is much larger as compared to this energy of the particle. We will make this assumption. Under this assumption, if you assume this, then Q becomes approximately equal to, if V is much larger than E, I can ignore this E. So, Q will be approximately equal to 2 mV, and the ratio P by Q is now equal to the square root of E by V, and since we have assumed that V is much larger than E, this ratio is much smaller than 1. So, in our calculation, we are going to make this assumption throughout, not that this assumption is essential to calculate tunneling probabilities, etc. Such tunneling calculations can be done in a very general situation where the potential energy is comparable to the energy of the particle. It can also be done in a more general situation where we do not have a step barrier, but we have something more general which looks like this, and the particle has a smaller energy. But for mathematical simplicity, we shall make these assumptions. We shall assume a step barrier, and we shall assume that the energy is much smaller than the height of the potential. The potential is much larger than the energy of the particle. So, it is a very high barrier. We are going to assume, make these two assumptions. These two assumptions make the calculation a little simpler. So, with these assumptions, we now have to apply the boundary conditions, and that will allow us to relate these, give us relations between these coefficients. So, let us write down the boundary conditions, one for the boundary between region 1 and 2 and another for the boundary between region 2 and region 3. So, let me write down these boundary conditions. So, we have written the boundary conditions. I shall refer to this as boundary condition 1. I shall refer to this as boundary condition 2. So, let us apply these boundary conditions first to the boundary at x equal to 0, the boundary between region 1 and 2. So, we will consider the interface between region 1 and region 2, the boundary at x equal to 0. So, the first boundary condition is that the wave function should be continuous across the boundary. So, the first boundary condition is that the wave function should be continuous. So, at x equal to 0, psi 1 should be equal to psi 2. We really do not have to bother about the time part because they are already the same. So, we have to set x equal to 0 here and here. time part is the same, so it cancels out. So, let us set x equal to 0 in psi 1. So, what it tells us is that a1, if I set x equal to 0, this becomes a1, this becomes b1. So, at x equal to 0, psi 1 is a1 plus b1. I am not bothering about the time part because it is exactly the same for all 1, 2 and 3. So, on the left hand side, the first boundary condition matching the wave function at the boundary x equal to 0, on the left hand side the wave function has a value a1 plus b1, and this should be equal to, on the right hand side is region 2. We are considering the boundary between region 1 and region 2. So, on the right hand side at x equal to 0, set x equal to 0 here and here, this term becomes 1, this term also becomes 1. So, I have a2 plus b2. So, this should be equal to a2 plus b2. So, this is the first boundary condition where we have matched the value of the wave function on the two sides. Now, let us match the spatial derivatives of the wave function on the two sides. So, we have to take the wave function in region 1, calculate its spatial derivative and then set x equal to 0. So, the spatial derivative of this is the same function multiplied by I p divided by h cross. If the spatial derivative of this is the same thing multiplied by minus I p divided by h cross. So, I can say that the spatial derivative of the total is going to be at x equal to 0, it is going to be p I p by h cross. You see, I can ignore h cross because it will occur here also when I differentiate it. So, I am not going to bother about the h cross. So, the spatial derivative of the left hand side at x equal to 0 is going to be I p a1 minus b1 is equal to the spatial derivative of the right hand side is going to be the spatial derivative of this is going to be minus q by h cross into this, and here it is going to be plus q by h cross. So, if I take the minus q common outside, I will get a2 minus b2, h cross is being cancelled out from both here and here. So, this is equal to minus q a1 minus a2 minus b2. So, this is the spatial derivative of the wave function on the right hand side, this is the spatial derivative of the wave function on the left hand side of the boundary between 1 and 2. Right, there will be a difference of minus sign between these two, a difference of minus sign between these two. I have taken minus q common outside after differentiating. So, this becomes a2 minus b2. I have taken ip common outside after differentiating this. So, this will be a1 minus b1, and this is the condition that I get. Now, we can simplify this expression slightly and write it as a1 minus b1 is equal to, I will divide this by ip, minus 1 by I is I. So, this will become I q by p into a2 minus b2. So, this gives us relations between a2 and b2 with A1 and B1, and we could, it is quite obvious that we can solve both of these and get A2 in terms of A1 B1. We could also get B2 in terms of A1 B1, which I had told you we could do, but we will not do this right now. Let us look at the other boundary that we have in this problem. In this problem, we have two boundaries, one over here and the other over here. So, let us look at now the boundary between region 2 and region 3. This boundary occurs at x equal to a. The left hand side is region 2, the right hand side is region 3. So, at this boundary we will now apply the first boundary condition, the fact that the wave function should be continuous. At x equal to a, psi 2, what is the value of psi 2 at x equal to a? Psi 2 at x equal to a, so we have to set x equal to a here, x equal to a here. So, let me write it down. We are looking at the boundary at the interface at x equal to a, and matching the boundary conditions, the left hand side, on the left hand side we have a2 e to the power minus q a by h cross plus b2 e to the power q a by h cross. These are the two terms at x equal to a, and this should be equal to the wave function at x equal to a in region 3. So, in region 3 we will have a3 e to the power I p a by h cross plus this term is 0. So, we really do not have to bother about it. So, this term, this should be equal to a3 e to the power I p a by h cross. So, we have applied the first boundary condition at the boundary x equal to a. This is the interface between region 2 and region 3. Let us now apply the second boundary condition. The second boundary condition is the requirement that the derivatives should be same on the left and the right hand side. So, we have to differentiate this and set x equal to a. If I differentiate this, I will get a minus q here, I will get plus q here. H cross will be there both here and here, so I can cancel it out. So, let me take this minus q common outside, and what I get when I differentiate is minus q a2 e to the power minus q a by h cross minus b2 e to the power q a by h cross is equal to, if I differentiate the right hand side, if I differentiate this wave function in region 3, so this I should denote 2 here. In region 3, if I differentiate the wave function, I have only this part. I will pick up a factor of IP. So, what this should be equal to IP, then I have A3 e to the power I p a by h cross. So, we have now got the two boundary conditions at the second boundary x equal to a, and we can simplify this one step. So, let me simplify it one step. If I simplify it, then what I get is a2 e to the power minus q a by h cross minus B2 e to the power QA by H cross should be equal to minus I P by Q A3 e to the power I P A by H cross. So, this has been obtained from this. It is exactly the same, just that we have taken this factor of minus q onto the other side. So, we now have two boundary conditions at the boundary x equal to a, and again we can eliminate the A3 here and write it in terms of these. We shall so what we have done now is that we have a free particle wave function here, we have the solution in this region and we have the solution in this region. We have to match the boundary conditions at this boundary and this boundary. The boundary conditions are two. The wave function should be continuous, its first derivative should be continuous. At the boundary x equal to 0, we have these two conditions. At the boundary x equal to a, we have these two conditions. In tomorrow's lecture, I will take these boundary conditions and use them to calculate the probability that the particle can tunnel through this potential barrier. That is what I am going to take up in tomorrow's lecture.